Figure 3 shows part of a curve C with the parametric equations x equals tan theta, y equals sine theta, where theta is between 0 and pi over 2. The point P lies on the curve C and has coordinates root 3 and half root 3. Find the value of theta at the point P. So at the point P, I know that the x coordinate is root 3, and I know that the y coordinate is a half root 3. So if I make my x equal to root 3, I find that tan theta has to equal root 3. So if I do tan inverse of root 3, I find that theta is going to equal pi over 3. And just double check that, substitute that into the y equation as well, just to make sure. And yes, we do find that we get root 3 over 2, or half root 3. So theta equals pi over 3 at that point. The line L is a normal to the curve at point P. The normal cuts the x-axis at point Q. Show that Q has the coordinates k root 3, 0, giving the value of the constant k. So point Q is here. We know that's where our normal intersects the x-axis. So let's work out the equation of the normal first. To do that, we want to work out the gradient function of the curve so that we can get the gradient of the tangent at P. Once we've got the gradient of the tangent, we can then do the negative reciprocal to get the gradient of the normal, and then do y equals mx plus c to get the equation of the normal. So, our gradient function for the curve, when we're in parametric form, it's dy by dt divided by dx by dt. When I differentiate x, differentiating tan with respect to theta, I'm going to get sec squared theta. Differentiating my y function, so differentiating sine theta, I get cos theta. So I'm going to get cos theta over sec squared theta, which is the same thing as me saying cos theta over 1 over cos squared theta, because I know that sec squared is the same thing as 1 over cos squared. To simplify this, let's multiply top and the bottom by cos squared to get rid of that fraction off the bottom. So those will cancel out and I'll just be left with cos cubed theta. That is my gradient function. At point P, I know that theta is pi over 3. We found that in part A of the question. So if I substitute that into my gradient function, so cos pi over 3 cubed, I get 1/8. So the gradient of the curve at that point is 1/8, which means the gradient of the normal will be the negative reciprocal of that. So that's going to be minus 8. I can now do y equals m x plus c. I know it passes through point P, which is this coordinate, so let's substitute that in. So I get root 3 over 2 equals minus 8 root 3 plus c. So therefore, c is going to equal 17 root 3 over 2. So the equation of my normal then is y equals minus 8x plus 17 root 3 over 2. Finally, we can say at point Q, at this point here, we know that y equals 0. So if I make my y equal to 0, and now I'm going to solve this equation to find out what x is going to be. So move the 8x to the left-hand side, divide through by 8, and I'm going to find that x is 17 root 3 over 2 times 8, so 16. So that's my value for, that's the x coordinate. So just comparing that to what we were told in the question, we can hopefully see clearly there that k is 17 over 16.